Okay, so what we have here is a rotating disc, and you can see what's happening is it's rotating in the vertical plane. So think of it like something that's cutting some wood or something like that. And so it's rotating in the vertical plane, right? And so but the like the bar, so to speak, is horizontal, but it's rotating vertically. It's rotating up and down. Okay, so what's happening is this thing's rotating, right? And this round blade has a radius of 0.12 meters. Okay, and so what's going to happen is, and it has an acceleration of 2, which is this alpha down here, is 2 revolutions per second squared. So that's how so this thing is accelerating, right? And so so this thing is starting out at zero velocity. So it has no velocity. Someone turns it on, and it's going to start accelerating, like I said, at 2 revolutions per second squared, right? And so it's going to go faster and faster and faster and faster. Okay, but after it has completed 100, that's the second piece right here. So I already talked about its acceleration, which is here, and then here I'm talking about the theta means this blade has spun 155 revolutions. Okay, once it's done that, so remember it started at zero speed, no velocity, and then it's going to accelerate. Like the more it spins, it's going to go faster and faster and faster. And once it's gone 155 revolutions, something's going to happen on it, and it's going like a piece on it is going to break off, and so that's this top piece up here. Right here where it says V0. So some piece of it's going to break off at the top, and it's going to start, and the piece is going to fly off. Okay, obviously unintentionally. It's going to fly, and it's going to make some ballistic trajectory, and it's going to hit the ground. Okay, I forgot to also mention this distance here from the top to the bottom is 0.820 meters. Okay, so this problem is really, it's 2 problems. One, it's a circular, like a rotation problem, and then it's just a kinematics problem. Okay, like a ballistic problem. Okay, so basically you have to do the circular part first, and then the second part is you have to do the kinematics, the ballistic stuff second. Okay. So what I'd like to do is I want to convert all this stuff into like normal units. So we have meters, which is good, but acceleration, which is alpha, obviously that means angular acceleration. And so what I want to do is which is fine, but it's 2 revolutions per second squared. So what I want to do is convert that into radians per second squared. So of course, all we have to do is multiply that, since say 1 revolution is equal to 2 pi radians, and then we delete that, get rid of that, and then what we have here is 2 times right here, 2 times 2 is 4. There's still pi is still there, and that's it. And then it's 4 pi radians per second squared. Okay, so that is its angular acceleration. Now, the theta, remember the piece is going to break off once it's made 155 revolutions. I just want to turn that into radians, okay? So we're going to multiply that. So how can I make that into radians? Well, we can just say 1 revolution is equal to, once again, 2 pi radians. All right, we'll get rid of the revolutions. And then basically we should just say 2 times 155, which of course is 310. We're going to keep the pi, and we'll have sorry, not radians. Yeah, just radians. So once this, so what we're going to do is this thing, so the blade's going to start at 0, no speed. It's going to start accelerating at 4 pi radians per second squared, and once it's done 310 radians, that many like revolutions, so to speak, that many degrees or radians. Once it's moved that much, then a piece is going to fly off. Okay, so let's also make this right here like that. Okay, great. Also, about what we might want to know is how long is it going to take for this thing to hit the ground? So there's like a little metal piece, let's say, because it's a metal blade, and so once it breaks off, it's going to hit the ground, right? Now, do I need to know? So I have v0 is its velocity. Now, this thing is only going to go it's only going to go horizontal. So there is no vertical component to it. So if I want to know how long is it going to take to hit the ground, do I need to know its horizontal velocity? No. The only thing I need to know is its velocity up and down, I need to know what it looks like, how to model it in the y direction, and its y velocity is 0, right? Because it's not moving in y initially. And do I know it? And do I know its acceleration in y? Yeah, that's gravity. Okay, so because this thing is moving initially, it only has a velocity in the horizontal direction. It has no vertical one. Therefore, I can go ahead and figure out how long it's going to take to hit the ground. Okay, so what I'm going to do is I'm just going to make a little graph just to make it nice and simple. And I'm going to say the velocity in y, because that's what we're talking about here. Is time is on the x-axis, and yeah. And then I can do this too. And so so what's the initial velocity in y? None. So we're going to put it here at 0. And what's the acceleration? Well, there's only gravity, right? And gravity's pulling down at 9.8. So of course this slope here, that slope here, is negative 9.8. And then, well, it's 9.8 meters per second squared, of course. But remember that when you're doing velocity versus time, this line right here represents acceleration, right? That's not represent acceleration. So negative 9.8, you would say negative 9.8 t. Okay. Well, technically you could say plus 0 because 0 is the y-intercept, but obviously you don't actually need the 0. It's superfluous. So what's going to happen? This thing is going to go down. It's going to go down like this, and at some time t, here sometime t, so that's this point here, right? Something's going to happen. Well, it's going to hit the ground, and when it hits the ground, so how far has it traveled vertically before it hits the ground? Well, you can see right here that the vertical distance is 0.820 meters. So it's going to travel 0.820 meters before it hits the ground. So what I can do here in this graph is I can say 0.820 meters. So remember, in the velocity versus time graph, the area under the curve represents the displacement, like how much this object has moved, how much it's been displaced. And so yeah, so it's 0.820 meters. So that's how far it went. Okay, so and then I know this, of course, is 0. And then I know this here is t. In this direction, this is like t seconds. Right? And so what I'm trying to do is I'm trying to figure out how long it's going to take. So do I know what that is? Yeah, so what I can do also is I can go out to the line here, and I could say, what is this point here? Well, this is negative 9.8 times t. So this is negative 9.8 times t, whatever t happens to be. Like, I don't know what t is. Let's say t is 5. Let's say seconds. Let's say t is 5 seconds. Well, then there'd be 5 times negative 9.8. But I don't know what it is. But now what I could do is I can make an equation where I can do. So do you see a triangle here? All right, here's a triangle, and I know so the area of a triangle, the area of a triangle is what? 1/2 times base times the height. Well, I know the area. It's already here at 0.820. 0.820 and then you do 1/2 is 1/2 times the base. What's the distance of the base? Which is t, and then times the height, and that's well, it's actually -9.8 t. Now, if you look at this, you see there's a negative on the left, but then there's a positive on the right, so you're going to end up with a negative, and we're looking for time here. So what's the problem here? Well, because actually this area is underneath the 0 line, right? So if you were to like look at, so this line is 0, right? So any area that's under there, mathematically speaking, is negative. So what you could do is you could just put a negative in front, because that's like quote unquote negative area, right? And so yeah, so what we can do here is you can multiply times 2. Basically, you don't need the negative because it's negative on both sides, so you can just get rid of that. And then you can multiply 2 times 820, which is 1.64. 1.64 after you multiply times 2, right? If you multiply this whole thing times 2, then you have with 1.64, like that. And then you're going to divide by 9.8, and then you're going to end up with t times t, of course, is t squared, and you're going to take the square root of that, and then you're going to end up with just t. T equals 0.41 seconds. So that's how long it's going to take to hit the ground. Once it breaks free of this blade, it's going to take 0.41 seconds for it to hit the ground. Okay, and of course we're going to need that, not now, but we're going to need it in a minute. Okay, so we're just gonna hold on to that. So basically, what I did was I'm using physics concepts. So I was like, oh, because this triangle, the area represents the distance I traveled at 0.820, and yeah, then I know t, and then I know the slope because I know acceleration due to gravity, blah blah blah, and you put it all together, and yeah, you can get your time. Perfect. Okay, so what I want to know is, so I have v0, right? That's the velocity of this like piece of metal that broke free. I know its y velocity, 0, but do I know its x or horizontal velocity? No. So what I want to do though is, remember this blade started at 0 velocity, but either an angular velocity or linear velocity, it doesn't matter. They're both 0, and it's going to accelerate, go faster, and then then it's going to break off. It's going to be going some amount of speed. So I need to figure out what that is. So what I want to do is I have angular acceleration. Can I take angular acceleration and then turn that into a velocity? Okay, so what we can do is this. I'm going to create a graph here. And I'm going to write omega. That's a W? No, that's omega. It sort of looks like a W. And I have t. So remember, omega is just velocity. It's angular velocity. It's just radians per second. And then t, of course, is time. So remember, it's velocity. So what was the velocity initially of this the whole thing? Well, it's 0, right? So this initial velocity is 0. So I'm going to put this thing at 0. And then the second thing is, do I know its acceleration? Yeah, I already had it up here. It was like right above here, 4 pi radians per second squared, right? So, and that's constant. Is it changing? No, it's just a constant value. So I can just make some sort of line here, and then I can say omega as a function of t, meaning the velocity, the angular velocity as a function of time is 4 pi times t, right? 4 pi is actually the slope, but if I want to find out what it is over time, I need to add the t, okay? And of course you could add a 0 because that's the y-intercept, but we don't actually need it. Okay, so so that's how I'm using acceleration. So I had 4 pi radians per second squared, and I can just put it right here because the slope of this, remember, when you have velocity versus time, that line that you write, that slope is acceleration, and we already have it. It was given to us. And there's going to be some time t right here. And at some time t, something's going to happen. It's going to break off. But how far have I displaced? Well, this is angular stuff. So you're not moving in x, you're moving in angles, right? You're moving in angles. So in linear stuff, you would have velocity versus time, and you're moving in x. Oh, I went 1 meter, 2 meters, 3 meters, 4 meters. But this is angular stuff. You're not moving in meters, you're moving in angles, right? You're moving in degrees or revolutions or radians, okay? So how many things have I moved? Well, I moved 310 because that's what it says right here. 310 is how much I moved. So I can do 310 pi radians. That's how much I've moved. And yeah, let me just erase this guy. Okay, so here is 0 seconds, and this is t seconds. Because I don't know what the time is. I don't know what the time is. And then here, of course, what's this? This is 4 pi t, right? It's just 4 pi t. And then once again, just like the other one, the one that we it's very interesting how this thing kind of comes up over and over and over again. But you have another triangle, right? And you can see I have the area, area equals 1/2 times base area equals 1/2 times the base times the height. The area, of course, is 310 pi, like that, radians, equals 1/2 is 1/2. Base is t again, and the height is 4 pi t, 4 pi t, right? And what you could do is you could see you have pi on both sides. You could imagine dividing by pi, right? And so you get rid of that pi here. And then there's a half over here, and then there's a 4. So half of 4 is what? Is 2. So you get rid of that, and you have a 2. And then you have a t and a t, which becomes a t squared. Something like that. And then over here you have 310. 310 equals, and then you just divide by 2, like that. Get rid of the 2 over here, and then you can take the square root of that. Yeah, that's right. And you're left with t equals the square root of 300. Well, if we go back a little bit, what's 310 divided by 2? It's 155. So you say t equals the square root of 155, which happens to be 12.45. 12.45 seconds. Sorry, I was just thinking. So 12.45 seconds. Great. So what we can do is, let me change this to this. So what does that mean, 12.45 seconds? Well, that's right here, 12.45 seconds. That means when this thing was started spinning up, it spun around and around and around for almost 13 seconds, a little less than 13 seconds. And then at that time, 12.45 seconds, that piece broke free. But then how fast was it going? Well, you already have the formula. It's omega as a function of t, or velocity as a function of time. Remember, it's 4 pi t plus 0. Once again, I'm just showing you that the 0 is just a y-intercept, which we don't have. And all you have to do, of course, is just pass in 12.45 into that function. And if you do, you get 156 radians per second. Radians per second. And so that's how fast it's going when it breaks free. So when it breaks free, it's going 156 radians per second. Let's do that, so that's its angular velocity. But then what I want to do is in order to do this this ballistic work, I need to actually convert that angular velocity into a linear velocity. And so all you have to do in order to find the linear velocity, which is just v, is the angular velocity times the radius. So, right, the longer or the larger the radius, the more your linear velocity. And so I have omega, right? I just did it, 156 radians per second, times how big is the radius, and that was already given. That's up here, 0.12 meters. 0.12, of course that's meters. And so if you do that, then you'll get the actual velocity, 18.72. 18.72, and that's in meters per second. So that's its linear velocity, which is that. That's its linear velocity. And then the final piece of the puzzle is, well, how far did it go? Well, I know its velocity is, its linear velocity is 18.72 meters per second. And now, do I know how long did it go? Yeah, because we calculated it right here. Right, we calculated it right here when we were trying to, when it dropped down, we used gravity. So remember, it took 0.41 right here. It took 0.41 seconds for it to hit the ground. So that's how long it was in the air. That's how long it was detached, so to speak, from the mothership, was 0.41 seconds. So down here, it was going 18.72 meters per second for 0.41 seconds. And all you got to do is put that together. Remember, because distance is equal to velocity times time, because velocity is in meters per second, and then time is in seconds, right? the seconds go away, and all you're left with is just meters. Yeah, and so velocity, of course, is 18.72 meters per second, and then my time was 0.41 seconds. Let's just put some equals in here for fun. And then I end up with 7.67 meters. And yeah, maybe let's put a D here for posterity's sake. Let's do some red, like that. And so yeah, so in recap, this metal thing is going to start at zero. It's going to start spinning faster and faster. And at 12.45 seconds, it's going to break off. And when it breaks off, it's going to be going 156 radians per second, or it's going to be going 18.72 meters per second. And how long is it going to be traveling at that velocity? Well, it's going to be traveling at that velocity for 0.41 seconds. If you put those two together, you end up with 7.67 meters. So in this problem, like I said, what I did is I used like angular kinematics, like degrees, omega, which is like radians per second, or alpha, which is like radians per second squared, or whatever. And we did a bunch of kinematics problems in the angular world, and then converted that over into linear numbers, like linear velocity using meters per second. So it went from the angular world to the linear world. And then we did some basic ballistics problems, because this like little metal piece, it performed a ballistic trajectory once it was free, so to speak, from the main piece. Once it broke free, it just followed a basic ballistics trajectory. And so we were in the angular world, did some solving there. Then we transitioned over to the linear world, and then from there we did basic ballistic measurements, and then that's it. So this problem, like I said, it's a pretty cool problem because it involves a lot of different, pieces of physics in order to solve the problem. All right, that's it.